We are the Gujarat Technological University. Since its inception over a decade ago, GTU has been empowering young and curating minds to realize their true potential. Over 4 lakh inspired students are enrolled with one of the premier academic universities in India.
So today we are learning one-way simply supported slab. For that, let's share my screen. I have my written notes. So for one-way simply supported slab, this is a cross section of the slab. Okay, this depth is called overall depth, and this depth without including this clear cover is called effective depth. Okay, so this point to this point is called effective span, and this is the effective length. Okay, so what is the data? So data is like they have given the slab of 3.2 meter to 9.2 meter. The slab is resisting on 300 mm thick wall, and live load and uh, Laminate and floor finish is not given, but you can assume finish as 1 kN per meter square. M20 and FE4.5, this data is given, and they have mentioned that you have to check for deflection and cracking, right? Okay, and draw reinforcement details. So what we are going to do, we will design overall depth. So particular design means we have justified what will be the overall depth, what will be the effective depth, what will be the A estimates, what will be the area of cross section, and what will be the area of steel, or area of steel in main distribution way. So in this one, this parallel line to its span is called main reinforcement. Okay, this is the main reinforcement, and the dot, okay, means the perpendicular to this main reinforcement's direction is called distribution steel. So first step would be effective depth. Okay, they have mentioned that it is a 3.2 meter to 9.2 meter. Let's take 3.2 meter here to here and 9.2 meter this corner to this corner. So Lx is 3200 mm. Then L by D. So what will be the L by D? L by D means span to depth ratio. So how can we decide the span to depth ratio? So it is given in 456 in page number 37. Okay, this clause number 23 to 1, it is given the basic value of span to effective depth ratios for span up to 10 meter. Our span is too small, it is less than 10 meters, so we can consider these things. So for cantilever, it will be 7 length to depth ratio. For simply supported, it will be 20. So we have simply supported B, so we can take it, and there would be L by D into modification factor. So how can we find modification factor? From figure number 4, page number 38. Okay, in this figure, in this graph, we can find out the modification factor. The modification factor just depends upon how much percentage of steel we have assumed. So we have assumed 0.6 percentage of steel. This vertical line is called modification factor, and there are the curves. Curves about what? Curves about Fs. Okay, so Fs you can find out in just below the graph. It is 0.58 into Fi. Fi is given, the area of cross section of steel required and provided. We can take both as the same. So this ratio will be is equal to 1. So 0.58 into F5, we can have this value. Okay, so just it's a tip from me. So if my Fs is equal to 0.58 into F5, okay, so if F5 is equal to 250, then Fs will be 145. Then F5 would be 415, then Fs would be 240. And if it is 500, then it will be 290. Okay, so it is a quick setup for identify perfect value of fs without using the cal. See, if you want you can remember, if you don't want to remember it's okay. So in my case fs is equal to 1.15. Sorry, modification factor is equal to 1.15 because my sf lies between 240. So let's have 240 curve and assume 0.6 percentages still. Let's take this curve in this side, and this side would be, and this side would be this one. So we are assuming 0.6 percentages still. So modification factor would be 1.15. Okay, it is as simple. You can take a round figure for that. Then after, let's have LDL length. We know that what will be the length, and D would be effective depth. So we can find effective depth. So in general way, effective depth of slab would be 150 mm. It is a standard. Okay, if you have something this type of figure, so fraction figure, so you can convert it to round figure as 150, 120, 140 as you want. So assume 10%, 10 mm bars. Okay, so we are assuming 10 mm bars for main reinforcements. Okay, one thing I want to clarify that the span. Okay, what will be the cross section from which side? Okay, so we are taking cross section from this side. Okay, from LX. Okay, it is called LX 3.2 meter. It is called LX, and largest side is called LY. That is a basic thing you need to know. Then let's find overall depth. Overall depth will be the total one, total effective depth plus half of the diameter of bar and plus the clear cover. So minimum clear cover required for slab is 20 mm. So I am using here 20 mm. Okay. If you want to find out nominal cover for different cases, you can find out a table number 16A 456. Okay. Here I mean to page number, it means I am talking about only IS 456 2000. I won't repeat it every time. Then step number 2 is effective span. Okay, so effective span, for that we have a clause on page number 32. Okay, so effective span would be, okay, let's have page number 42, clause number 22 to A. So here it is page number 42, 22AA. Okay, okay, this one, 22 to 8. Okay, simply summarized, the effective span of the member that is not built integrally with support shall be taken as, okay, and here is the story begins. The clear span plus the effective depth or slab, or number 2, beam or center to center support. So we have two options to find out effective span. First one is L plus D, and second one is center to center of support. So my L is 3200 plus D I have calculated. Center to center support is like here. Okay, center to center support, how can we find? We have 300 mm resisting wall, okay, below the slab. So half of this wall and half of this wall, we can find out the total length. Okay, so it is 3 for those. So smaller of these two value will be the final of effective span. So let's look ahead. Step number 3, load calculation. So load calculation would be per meter. Okay, if I'm talking about width, then width, always the width B would be 1 meter or 1000 mm. Okay? So first one, dead load is equal to area into density. Okay, each and every time in RCC, if you are finding something dead load of some substance, so it will be area into a density of the material. So concrete density is 25 and area is B into D. I'm not talking about length. Okay, I'm talking about cross section area. So in cross section area, it will be width and depth. So which depth should we take? The overall depth should we take, which is 175. So floor finish and live load. Okay, live load is given. Then after summation of all three loads, then factor it from 1.5 because we are doing limit state design. Then again the tips will be, yes, self weight of the section is d into d into the density of concrete. Hmm. So step number 4 would be bending moment. So it is a simply supported beam. Let's turn out it in a simple beam like we are using in structure analysis examples. So if it is simply supported and it is UDL, okay, so each and every load, okay, each and every dead load, floor finish and live load, it is acting on it as a UDL, it is as a kilonewton into meter. Okay, it is a kilonewton into meter. Then mu is equal to W L square by it. It is a simple formula for simply supported slabs to find out the moment. It is W L square by it. So we can have now bending moment. Then step number 5, effective depth for flexure. Flexure means basically the moment. Okay, you can take it as a moment sometimes. So in SP16, there is a formula for that. It's a limiting moment. It's called MU. So MU would be 0.38 FCK BD square. Though SP16 is not allowed in your curriculum or in your examination, but you can remember this formula as a limiting moment. Okay, so we can ultimately we are finding the D. Okay, if my depth is nearer to depth provided, so depth required is this, and depth provided is this one. So how much depth we are using for that? It is a 150 mm. Okay, and what is requirement for that? It is 77.5 mm. So in flexure, okay, in flexure or in bending, the slab is safe. Then after, okay, and don't forget to add 0 point sorry, and don't forget to add a 10 raised to 6 as it is kilonewton into meter, and our rest of the dimensions are in mm. Okay, most of the students make mistakes in this step. Okay, one also there is one tip for you people is if there is 10 diameter of bar, then the area would be 78.50. Okay, there is nothing like a rocket science. It is a pi by 4 b square. Okay, pi by 4 into 10 raised to 2. So we can find out 78.50. If it is 8 diameter bar, then its cross section area is 50.20, and then it is 16 of bar, then it will be 201.6 square. It is a cross sectional diameters of the bar. You have to remember this for easiness of your example, because in examination you won't get time to complete all the sections. So it is beneficial for you to remember all these small steps. Then step number 6 is main still. Okay, main still we can find out from page number from SP16, but we have some formula for that. Okay, you have to remember this formula. It is not given in a code or anywhere. So percentage of still we can find out from this formula. Okay, so 50 FCK we have, it is 20 FY we have, it is 415. 1 minus under root 1 minus 4.6 into MU FCK BD square. Okay, if you are putting all values in your formula, then don't forget to add MU as 10 raised to 6 as Newton per mm square. So my percentage of still required for this bending moment or for this section is 0.215. Then AST is equal to PTBD. Okay, I have told you that if we are talking about B, then it will be 1 meter or 1000 mm. Okay, so we are using this one. Then D is equal to 150 and AST is 0. So here are some tips for find AST. Okay, so now the spacing. Okay, in slabs, we are not talking about number of bars and all like beam. We are talking about the spacing. Okay, so how much spacing between two bars? It is important. Okay, so spacing generally important to deflection. Okay, if your spacing is too much, then your beam will have too much dead load, and your spacing would be too wider between two roads, then your deflection chances of deflection will be more. So you need to clarify basic spacing or perfect spacing for your design. So spacing is equal to capital AST upon small ast. So what is capital AST? Small ast. Small ast is nothing but the area of the one bar, cross section area of the one bar. Either it is a 10 mm, 8 mm, or 16 mm. But in the first step, we have taken it as a 10 mm bar. So thousand is for meter. Okay, it is indicating a meter is equal to 1000. So we have 10 mm bars of diameter. Then AST provided, we have provided AST as 3200 year one. Then we have 250 mm. Okay, so distance between two parallel bar would be 240 mm. Okay, so just reverse the just reverse this thing and find out if it is 240 mm, so what will be area provided. Okay, there is a difference between area required and area provided. Okay, this is called my area required according to my calculation, and what is provided, I am providing the area considering limit state design. It is called area provided. Okay, it is nothing. So area provided is 327. So basically I'm using 10 mm diameter of bar to 240 center distance, and my total AST is 327 mm square. Like this only we can choose distribution steel perpendicular to his main bar. So you can have clause number 26521, which is called how many percentage of steel is required for cross sectional area or for distribution steel. So they have clarified that PT 0.12 would be okay for distribution steel in one way simply supported beam. So AST would be PT BD. Okay. So in here D would be the overall depth, not the effective depth. So same procedure as we done in a main distribution bar. Okay, and then we proceed to check. So for this I have used 6 mm bars, 130 mm center spacing, and AST is 217 mm square. And for cracking, okay, for cracking go to page number 46. In cracking there is a clause for that. Let me show you. Okay, here is the clause for that. This one. Okay, 2633 in B slabs. For slabs, the maximum distance between bar in tension. Our slab will once have tension in the slab span, so it will be okay for deflection or spacing. So what they are written? They have written the distance between parallel main reinforcement bar shall be more than parallel bar shall be one sec. Parallel main reinforcement bar shall not more than 3 times or effective depth of solid slab or 300 mm, whichever is small. It is about main reinforcement here written, and it is about distribution one. Okay, so both clauses are different. So let's jump it. So for main steel, either it is 3D or either it is 300, smaller of this value. And for distribution, either it is 5D or either it is 450. Okay, whichever is smaller. So spacing. Also for cracking, we are checking the spacing. Okay, so whichever is smaller, it is 300. Okay, so 300 should be less greater than of taken spacing. Okay, what spacing I have taken for main cell, it is 240. Okay, my limit is my maximum limit is 300 mm. Okay, if there is a spacing more than 300 mm, then my slab would deflect. So it is okay, and same for distribution bars. It is okay. We have taken 450, but sorry, we have taken 150, but the maximum point is 450 mm. So it is okay. Then another one is check for deflection. For check for deflection, it is so simple. I'm repeating the step number 1, that allowable LD. Okay, there is two type of length to depth ratio: allowable and actual. Okay, so allowable is depends upon the code and actual is depends upon the figures. Okay, so allowable is 20 into 1.6. So how can we find out 1.6? Because we have PT. Okay, in the first step we have assumed the 0.6 percentage of PT, but now I have the percentage of steel as I have calculated in step number 4. So PT is 100 AST upon BD, like AST is equal to PT 100 PT upon 100 into BD. Okay, I am just informing it. Then oh okay, so I got my modification factor. My PT is 0.2. Then I can find modification factor from figure number 4. So my allowable length to depth ratio and my actual length to depth ratio. Okay, so my actual length to depth ratio would be less than to allowable length to depth ratio. Okay, because I am allowing you to have length to depth ratio is 32, and I am putting it as 22.43 mm. So it is okay for deflection. The next one is check for shear. You can check it from page number 73 and 72. So for shear, it is a tau v and tau c. So ultimately, what is the scene? You should have tau v less than tau dash c. So for that, let's first have tau v. So for tau v, let's jump to page number 32. Sorry, 32 is 72. So for tau v, yeah, it is coming. Yes, this one. Limit state of Euler's shear. Okay, clause number 40.1. So tau v is equal to VU upon VD. So what is VU? It is not. It is separate thing, and D. So VU is equal to shear. So how can we find shear? So shear is equal to WL by 2 because it is simply supported. You very well know that simply supported beam have same reaction on both ends. So V means a total load we have, and L length we have, and by 2. So we can have 18.91. Okay, so if you are talking about L, so you can take L as a clear span. Yeah, I have mentioned here. Then B, if I'm talking about B, then you have to choose only 1 meter or 1,000, whichever is preferable. Then D is equal to 150 effective depth we have. Then 50% of bent up for shear resistance. Okay, so take it as a 50%. It is 136.5 mm square. Okay, why is it so? So let's jump to page number 73. So here is table number 9. Table number 9 is all you know, that in this column it has PT. Okay, 100 AST upon BD is ultimately percentage of steel according to my area of steel. That is a concrete grade. Okay, my concrete grade for this example is M20, and I this inner inner numbers are called tau c. Okay, because it is a design shear strength of concrete tau c. It is able to find out tau c. Then I have find out that PT is equal to 0.1, and my AST is equal to 163.5 mm square. FCK is 20 and tau c is 0.2. So let's check it. It's 0.1, and my concrete grade is 120 M20, so it is 0.2. So I have taken tau c as 0.2, 0.28 here. It is tau c 0.28. So how what is tau dash c? So tau dash is given in previous page. Yeah, clause number 42.1.1. It is said that for solid slab, the design shear strength for concrete shall be tau ck or tau dash c, in which k value is given from them. So overall depth is, my overall depth is 175 here. Okay, if it is between 200 and 175, then you have to do interpolation for that, and you can take in between measures, and k would be 1.5. So it is k is equal to 1.5, then tau dash c is equal to k into tau c, okay, as mentioned in clause. So generally it is tau v, my tau v was 0.126, and my tau dash c is equal to 0.35, which is okay. So now ultimately you have to draw cross-sectional diagram for this. You have to mention all the things. This one is bent up bars, the main distribution, main still and distribution still, the overall depth, the effective depth, the effective span, the clear span, all the things you have to mention in the simply supported beam. And that's it for the simply supported beam. If you are doing examples, then it is okay to have these steps, because you won't get time to complete all the things at a time. Okay? So I'm stopping. I'm stopping the video. See you next time.